Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist, and bilingual teacher of mathematics and physics from Brazil. And in this video, I would like to invite you to a conversation about the calculation of voltages and currents in both direct current and alternating current circuits. And for this purpose, I selected several problems from the most important examinations for electrical engineers in Brazil. Let's go to the first exercise. Exercise number 1 says, for the circuit of the figure, calculate the value of the current I. This is the question. Let's go to the solution. This is an extremely simple exercise. Observe that the voltage of the source is being applied directly on the 10 ohms resistor. In this way, the central branch will not influence the calculation of the current. The central branch would influence only if there were resistances between points A and B or C and D. Therefore, the current I is merely the division between the voltage of the source and the resistance of the resistor. And the value of I is 2 amps. Okay, my friends, and this is all for exercise number 1. Let's go to the next. Exercise number 2. What is the value of the voltage drop across the 3 ohms resistor? This is the question. Let's go to the solution. To facilitate the calculation, we shall use some labels. I'm gonna call this current here I1. This will be I2. This current here I'm gonna call I3, and the voltage at this node I'm gonna call V1. To calculate the voltage drop across the 3 ohms resistor, we may apply firstly KCL at node V1. In this way, the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. Who are the currents entering the node? They are I1 and I2, and I3 is the only current leaving the node, okay? In this way, I1 plus I2 is equal to I3. Now we have to write the currents in terms of voltage drops and resistances. How can we write I1 in terms of voltage drops and resistances? I1 is equal to 8 volts minus V1 divided by 3 ohms. And how about I2? I2 we already know, it is 3 amps, and I3 is the division between this voltage here and the resistance, V1 divided by 7 ohms, and this is the equation. It is simple. I am going to invite you to try to solve it in your house, and after solving you find that V1 is equal to 11.9 volts, and with the value of the voltage V1 we can calculate I1. Alright, we are going to do this. We know that I1 is equal to 8 volts minus V1. V1 is 11.9 volts divided by 3 ohms, and ultimately it is negative 1.3 amps. And what does it mean? This negative sign here means that instead of going to the right, actually this current is going to the left in the opposite direction. This is not wrong. This negative sign here is not wrong. Simply that the current is going in the opposite direction. With the value of I1, we can calculate the voltage drop across the 3 ohms resistor. And in this way, V is equal to 1.3 amps times 3 ohms, and this is equal to 3.9 volts. Alright, my friends, and this is what the exercise wanted us to calculate the value of the voltage drop across this resistor. And it is all for exercise number 2. Let's go to the next. Exercise number 3. Determine the value of the voltage of the source E such that the current I is 0. This is the question. Let's go to the solution. Again, we shall use some labels to facilitate the calculation. I'm gonna call this E1. This current here will be I1 and this I2. Alright? Note that for the current I to be 0, there must be no voltage drop across the 10 kilo ohms resistor. In this way, if there must be no voltage drop here, we conclude that E1 has to be equal to 80 volts. Now, applying KCL at the node E1, we obtain that the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. I plus I1 has to be equal to I2. We already know that I is equal to 0. This is the requirement of the exercise. In this way, I1 must be equal to I2. How can we write I1? I1 is E minus E1 divided by 20 kilo ohms. And how can we write I2? I2 is simply the division between the voltage at the node and the resistance E1 divided by 20 kilo ohms. In this way, if we solve, it is simple to solve, okay? They have the same denominator here. We can cancel this with this. And we find ultimately that E is equal to 2 times E1. And as E1 is 80 volts, E must be equal to 160 volts for the current I to be 0. And this is all for exercise number 3. Let's go to the next. Let's go to exercise number 4. Exercise number 4 now. Determine the voltage and the current at the 10 ohms resistor in the DC circuit shown in the figure when it is operating under steady state conditions? This is the question. Let's go to the solution. Remember that in DC circuits, in steady state, a fully charged capacitor behaves as an open circuit, and the magnetized inductor behaves as a short circuit. Thus, in steady state, the circuit will behave as this. Alright? In steady state, this circuit is converted into this. Now it is easy to calculate the voltage and the current. Observe that the current I is equal to 100 volts divided by 40 plus 1050, which is equal to 2 amps. And how about the voltage? Simply V, the voltage at the 10 ohms resistor, is simply the multiplication between the resistance of the resistor and the current passing through it, 2 amps. And this is equal to 20 volts. And this is all the exercise requested from us. Very simple. We simply need to understand that a fully charged capacitor in steady state behaves as an open circuit. Likewise, a magnetized inductor in steady state behaves as a short circuit, and in this way we can calculate what the exercise wanted us to calculate. And this is all for exercise number 4. Let's go to the next. Exercise number 5. For the circuit of the figure, what is the value of the current I1? This is the question. Let's go to the solution. And again, to facilitate the calculation and the understanding, I'm going to use some labels. I'm going to call this V1. This I'm going to call I2. And this I'm going to call I3. The value of I1 can be easily calculated by applying KCL at node V1. Observe that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. And what is the current entering the node? It is I2. I2 enters the node. And what are the currents that leave the node? I1 and I3. Next, we write the currents in terms of voltage drops and resistances. How can we write I2 in terms of voltage drops and resistances? Observe that I2 is 200 volts minus V1 divided by 10 ohms. And how about I1? I1 is V1 divided by 20 ohms. And likewise, I3 is V1 divided by 20 ohms. This equation is extremely simple to be solved. I'm going to invite you to try to solve in your house. And after solving this, we find that V1 is equal to 100 volts. Subsequently, we calculate the value of I1. The value of I1 is simply the division between the voltage V1, 100 volts, by the value of the resistance, and this is equal to 5 amps. And this is all for the discussion of exercise number 5. It is everything the exercise wanted us to calculate. Let's go to the next. Exercise number 6. For the circuit of the figure, what is the value of the current I in milliamps? This is the question. Let's go to the solution. Instead of using KCL and nodal analysis, we will use the equivalent resistance to find the value of the current. To find the equivalent resistance, we shall combine resistances in series and in parallel from right to left, and this is precisely what we are going to do. Observe firstly that these two 50 ohms resistances are in series. Thus, equivalent resistance number 1 is equal to 50 ohms plus 50 ohms, which is 100 ohms. Observe now that this 100 ohms appears in parallel with this 100 ohms. And how can we calculate the parallel combination between two resistances? It is equivalent resistance number 2 is the parallel combination between two 100 ohms resistances, and the rule of thumb that we use is the product over the sum. Therefore, it is 100 lots of 100 divided by 100 plus 100, and this is equal to 50 ohms. Observe now that this is in series with this. This replaces all this and appears in series with this, and it is easy. Equivalent resistance number 3, we simply add 150 ohms plus 50 ohms, and this is equal to 200 ohms. This appears in parallel with this. They will be in parallel because this replaces all this and appears in parallel with this. And as we did here, we are going to compute the parallel combination between these resistances using this rule of thumb here. Thus, equivalent resistance number 4 is 200 ohms in parallel with 200 ohms, and this is equal to 200 lots of 200 divided by 200 plus 200, and this is equal to 100 ohms. Finally, we observe that this 100 ohms is in series with that 400 ohms resistance. Thus, the final or total equivalent resistance is 100 ohms plus 400 ohms, and this is equal to 500 ohms. Now we can calculate the current. The current is simply the division between the voltage of the source, 150 volts, by the total equivalent resistance, and this is equal to 300 milliamps. And this is all the exercise we wanted us to calculate the value of the current. Let's go to the next exercise. Exercise number 7. The circuit shown in the figure has a DC voltage source with internal resistance Ri and an open circuit voltage E equal to 6 volts. When the source supplies a resistive load RL equal to 1 ohm, the voltmeter indicates a load voltage VL equal to 4 volts. What is the value of the source's internal resistance RI? This is the question. Let's go to the solution. If the voltmeter indicates 4 volts when the value of the load resistor is 1 ohm, we can calculate the current that flows in the circuit. I is merely the division between the voltage and the resistance, and this current is 4 amps. With this current, we can calculate the internal resistance, but firstly observe that E is equal to VRI plus VL. We already know E, 6 volts, is equal to VRI plus 4 volts. And in this way, VRI is equal to 2 volts. With the value of the current and the value of the voltage drop, we can calculate the value of the internal resistance. RI is simply the division between the voltage, 2 volts, and the current, 4 amps. And this is equal to 0.5 ohms, or, if you prefer, 500 milliohms. And this is all for exercise number 7. Let's go to next. Let's go to exercise number 8. Exercise number 8, calculate the value of the current I2 and the voltage on the node E in the circuit. This is the question. Let's go to the solution. Observe that we can easily find the value of E by applying KCL at the node. The sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. What is the current entering the node? It is I1. And what are the currents leaving the node? They are I2 and I3. Okay, in this way, I1 is equal to I2 plus I3. Now we write the currents in terms of voltage drops and resistances. How can we write I1? I1 is 10 volts minus E divided by 1 kilo ohms. And how about I2? I2 is simply the division between the voltage and the resistance. It is E divided by 2 kilo ohms. And how can we write I3? I3 is E minus 4 volts divided by 2 kilo ohms. And this is the equation. It is simple to be solved. I'm going to invite you to try to solve it in your house, and you're going to find that E is equal to 6 volts. With the value of E, we can easily find the value of the current I2. I2 is simply the division between the voltage and the resistance, 6 volts divided by 2 kilo ohms, and this is equal to 3 milliamps. And this is all the exercise requested from us. Let's go next. Exercise number 9. For the circuit of the figure, what is the value of the voltage between points A and B, and what is the value of the current I? This is the question. Let's go to the solution. Observe that as 3 times 0.67 is equal to 2 times 1, the circuit is balanced and no current passes through the central branch. In this way, we know that I3 is equal to 0 amps. As a consequence, VAB is equal to 0 volts. There is no voltage drop between points A and B. Let's calculate now current I. Observe that I is equal to I1 plus I2. I1 is 16 volts divided by 2 ohms plus 0.67 ohms, and I2 is 16 volts divided by 3 ohms plus 1 ohm. We can easily calculate this, and after calculating, we find that I is equal to 10 amps. Okay? This is all the exercise wanted us to calculate, and we find that the voltage between points A and B is 0. There is no voltage drop because the circuit is balanced, and we calculate easily the value of the current. Let's go to next. Let's go to exercise number 10. Exercise number 10, in the circuit shown in the figure, the capacitor is initially discharged. After the switch is closed, what will be the voltage across the capacitor once the circuit reaches steady state conditions? This is the question. Let's go to the solution. Observe that in steady state, the capacitor behaves as an open circuit, independent of the voltage across it. Thus, as there will be no current flowing in the right branch due to the capacitor, there will be no voltage drop across the 5.2 kilo ohms resistor. In this way, the voltage across the capacitor is the same as the voltage across the 8 kilo ohms resistor. The voltage across the capacitor is equal to the voltage here. So VC is equal to V1, and how can we calculate V1? Simply using a voltage divider. It is 15 volts times 8 kilo ohms divided by 12 kilo ohms plus 8 kilo ohms, and this is equal to 6 volts. And this is all the exercise wanted us to calculate. And this is all for this video, my friends. I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number. Goodbye!